So all of this has led us up to the transpose of a matrix. And the transpose of a matrix is found by switching the rows and columns. So if we have an m by n matrix and we want to find the transpose, the notation for the transpose is a t, and that t is a superscript. Think about it. It's not an exponent, but it's in the place where an exponent would live. So all we do is we switch the rows and columns. So an example, if we have matrix A is the matrix 1, 2, 3, 4, then A transpose is going to take that first row and turn it into the first column. It's going to take that second row and turn it into the second column. So it would look like that. If we had something, let's say the dimensions were a little bit more interesting. Maybe we had a 2 by 3. Then the transpose will be a 3 by 2. It's going to take that first row and turn it into the first column. Second row becomes the second column. So there's our 3 by 2 matrix. So it just inverts the rows and columns. So there's some properties that go along with this. So let's say we have A and B matrices where the sizes are defined for multiplication and addition. So like in property 2, they have to be the same dimensions. So A and B are both m by n matrices. Here, A would have to be an m by n. B would have to be an n by p matrix. So that multiplication would work. So let's kind of walk through these. So number 1, it says if we take the transpose of the transpose, we'll get that matrix back. So that one's pretty easy to see. Just for fun, let's go prove that one. So we're going to let matrix A be this matrix. So if we were to take the transpose of that matrix, it's going to invert those rows and columns. And then if we take the transpose of the transpose, then we're just going to get right back to where we started. And that is equal to matrix A. So we have proven our case. So if we look at the second property, it says the sum of the transpose is equivalent to, the transpose of the sum is equal to the sum of each matrix transpose. So let's, just for fun, let's go ahead and prove that one. This is a proof. So we have A plus B transpose. We're saying that's equal to A transpose plus B transpose. So we're going to let A and B be M by N matrices. So we've defined what they are. Now let's show what they look like. So A is going to look like this. And B looks like this. Put then in front of this so we have a complete sentence. So A plus B looks like that. Now remember, we need what that transpose is going to look like. So we're going to interchange the rows and columns. So there's my first row as my first column. Here's the second row. Notice those diagonal entries are going to be the same. So there's that sum. So now we could split apart that addition. Oops. And if we analyze this guy further, this is actually A transpose. And if we analyze that, that's B transpose. So you can see how that property works. That's a pretty cool one. Now the transpose doesn't really do anything with a scalar. A scalar is just, just a plain old number. So it's not going to do anything. And you can see that come out in that third property. If we have C times A times the transpose of CA, then that's going to be equal to the transpose of A multiplied by that scalar C. So let's demonstrate that one with some numbers. So here's a demo. We are looking at CAT is equal to CAT. So I'm going to let C I'm just going to pick the number 2. And I'm going to choose A to be a 2 by 3 matrix. Just so you can see it come out. It's just better than using like a square matrix. So if we look at CA transpose, then CA, if we take 2 and multiply it by that matrix A, it would be that matrix transposed, which would be this matrix. Now, if we look at C times A transpose, our C is 2. A transpose would look like this. And if we were to multiply that scalar in, we get that. So you can see how that's working. This is a demonstration. This is not a proof. This only shows it works for this specific instance where C has to be 2 and A has to be that matrix 1, 2, 3, 4, 5, 6. So a proof is different than a demonstration. Proof shows that it works for any numbers, for any scenario. Like we did above, we had a generic M by N matrix for A and B. We showed it works for every single case. Here, we showed just a very specific instance, but you can see how that's going to work. And if we wanted to prove it, we could go through and we could prove it generically. I'll leave that to you as an exercise to do. And then the last one. It says AB transpose is equal to B transpose A transpose. So notice what happens here. We're taking the transpose of a product, and that's equal to the product of the transposes in the reverse order. So let's demonstrate this one. Now this multiplication does have to be defined. I'm going to let A be a 2 by 3. So for that to be defined, I'm going to let B be a 3 by 2. So let's do this. Let's look at AB transpose. So if I multiply A times B together, I'm going to get a 2 by 2 matrix. And we're going to have to take the transpose of that matrix. I'm just going to write that T up here so I don't forget to take that transpose. So first entry is going to be 0 plus 2 plus 6. 3 plus 8 plus 15. 0 plus 5 plus 12, and 12 plus 20 plus 30. So now if we take the transpose of that matrix, we'll get this matrix. Now let's find B transpose A transpose. So B transpose would end up being a 2 by 3. A transpose is going to be a 3 by 2. And if we were to multiply these together, that was 0 plus 2 plus 6. 0 plus 5 plus 12. 3 plus 8 plus 15, and 12 plus 20 plus 30. So you can see how we get the same thing in both cases. The proof for this one is a little bit more tedious. So I'll post a worked out proof of this online so you can see it with everything written out. But this is definitely a good demonstration so you can see how that property works with real numbers.